Okay, so take a moment to copy this example down, and we'll discuss the solution. Okay, so let's take a look at this problem from section 4.1, related rates. It's a really fascinating section because you can do a lot of applied problems. And you know, the math you're learning it because you're going to need to do applied problems in various fields: engineering, chemistry, biology, sciences, you name it, economics. So, all right, in this problem at noon, ship A is 150 kilometers west of ship B at noon. That's at time 0. And then ship A is sailing east at 35 kilometers per hour, and ship B is sailing north at 25 kilometers per hour. How fast is the distance between the ships changing at 4 o'clock? So, what might be helpful to start this process? I mean, to work this problem, what's going to be very helpful? An image, that's right, Ian, a graph, a picture. So some of the problems, like the problem that we had done on last Wednesday from section 4.1, well, it's a problem involving the volume of a sphere. Let me just double check that. I believe that's right. Oh, inflating a balloon, a spherical balloon. And so we started off with a formula for the spherical balloon, the volume formula, and then we differentiated both sides with respect to time using implicit differentiation, and we were able to work through the problem and the related rates problem. But here, in this problem, what makes it a little different? Well, we need to find some formula for the problem. We need to find a formula for the problem. But you have to draw a picture to help you get the formula. Okay, it's not like, well, you like the problem where we were inflating the spherical balloon. We could get the volume of a sphere just because we know that formula, or we can look that formula up. Here, you have to draw some kind of picture to help you. And so I'll move to the solution here. So what I've done is I actually draw two pictures just to sort of help you get a feel for the situation. So you have ships A and B. And at noon, at time equals 0, this is the location of ships A and B. Okay, let me just add a little something to the picture. So ship A is 150, ship A is 150 kilometers west of ship B. And so at noon, this is what the ships look like. But then what's going to happen, we're curious about how fast the distance is changing between the ships later at 4 p.m. So we need to think about what these ships do over time. Well, they tell us that this ship A is sailing east. It's going east at 35 kilometers per hour. And so that's what I have here in the picture below. I have ship A, and I have it going east. Going east. All right. And also ship Y is sailing north at 25 kilometers per, I'm sorry, ship B is sailing north at 25 kilometers per hour. So, here's ship B, it's going north at 25 kilometers per hour. So at time t, this is what the picture is going to look like. Now, it's just it's not too much time t, but this is certainly what we would see. So the ship A is sailing east at 35 kilometers per hour. Okay, and it goes a distance x, right? It has to go a distance x. Well, then if the ship A goes east a distance x, it still would have to go a distance of 150 minus x to reach the point where B started at. And notice that x plus 150 minus x adds up to 150. That's, if I have an x here, then this distance here, if that's the distance there that ship A goes when it goes east, the remaining distance would be 150 minus x, because x plus 150 minus x equals 150. Okay, and then for ship B, I have that going a distance y. I can't relate the distance, the vertical distance that the ship be sailing north at 25 kilometers per hour. So, but I can't relate the distance it goes to the x at all. So I just have a variable y. And then of course, you know, and at time t, the ship A and ship B are going to be, you know, here's where ship A is, right on that blue dot. Here's where ship B is, right at that blue dot, right at that position. So at that time t, they're going to be a distance z apart from each other. And this is, of course, a right triangle. Are there any questions on the diagram? The diagrams, you know, as I'll mention, you'll have diagrams that you need to draw for other problems like this, but they can be a little different depending on the problem. But is there any question at all so far before I move forward? All right. All right. Well, now I know that dx dt is 35, positive 35 kilometers per hour, and dy dt is positive 25 kilometers per hour. Okay, and I'm going to need to make use of that. I mean, everything in the problem gets used. You know what I mean? If you're doing the problem right, you're utilizing all the usually you're utilizing all the information in the problem. But again, you know, I have a good picture, and I know my rates, dx dt and dy dt, but now I need a formula. Well, how would I get, what formula would I, you know, what could I use to get a formula here? Given the picture, what could I use to get a formula? All right, Zoe's suggesting the Pythagorean theorem. That's absolutely right. We have a right triangle here. Very good, Zoe. All right, well, based on the picture then, okay, based on the picture with that right triangle, 150, quantity 150 minus x squared plus y squared would equal z squared. That's by, again, that's the Pythagorean theorem. And many of these distance problems involve the Pythagorean theorem. Spell it right here. I think I'm getting a little better with this mouse. Not perfect, but are there any questions up to where we have the Pythagorean theorem? The sum of the two legs squared equals the hypotenuse squared. All right, Lynn's good. All right, all right. Well, now what should we do next? I mean, we made all this effort to get this equation. You know, we drew a nice picture, and of course, on the exam, I'm going to want to definitely see pictures for these kind of problems. Okay, that'll be important for full credit. I mean, what are we going to do? What are we going to do? What do we do with this formula? Okay, I like what Sebastian's saying. Implicit differentiation. All right, so we're going to differentiate both sides of this equation, but we have to differentiate with respect to a variable. What variable would we differentiate both sides of the equation with respect to? Good, that's right, Sebastian, t. And it makes sense because look at the rates. We have dx dt and dy dt. So we're going to differentiate both sides of this equation with respect to t. All right, let's move to the next page and take a look at that. Okay, so I differentiate this equation with respect to t. And of course, I'm going to use implicit differentiation, right? That's how I'm going to have to do this. Now, in the second step here, I'm using implicit differentiation, okay, and the chain rule. But, you know, implicit differentiation really is the chain rule. But, the distances from the diagram, x, y, and z, in that right triangle, I want to be careful, the variables, x, y, and z, which, you know, y and z are the two legs in the right triangle, and x is that other little distance, but they're all distances. They're all distances, and so they are functions of time, because the distance that ship A goes is dependent on how long it's been sailing. Similarly, the same for the distance that ship B sails. That's dependent on how long it's been sailing, and z as well. All the distances are functions of time t, and therefore this allows me then to use some implicit differentiation, as you see in this step. Okay, let me know if there are any questions. All right. So, all right. Well, now what I'm going to do is I'm going to just rewrite this equation with these derivatives in it. I'm going to just write it like this. So let me just see. I think there's one error. There's maybe an error here. Hold on one moment. Let me check something here. I thought I had one moment. One moment. Let me just see here, class. No, we're good. We're good. We're good. We're good. No, what I did here, I was focused on why this -2 was here. And that's because this -1, I brought out front there. And so, you know, now what we want to do is we want to solve for dz dt. Because the problem says how fast is the distance between the ships changing at 4 p.m.? Okay, well, if we go to the picture here, the distance between, I'm going to be a little bit careful here how I say this and write this. So at time t, the position of ship A is right there. It's moved the distance x. And the position of ship B is right here. Okay, and so the distance between them is distance z, that hypotenuse. Well, when they say then how fast is the distance between the ships changing at 4 p.m., they want you to find dz dt. Okay, are you comfortable with that? Are there any questions on that? All right, Betsu is comfortable. Yaki's comfortable. Good, good. all right, well then let's get back to back here then. So we want to, I mean, here is our equation. Whoops, hold on. Take the little thing off there. Here's our equation, and we want to solve for dz dt. That means, of course, I need to fill in, or what? I need to fill in an x value. I need to fill in the rate dx dt. I need to fill in a y value. I need to fill in the rate dy dt. Okay, but remember, they want you to find, they're asking how fast is the distance between the ships changing at 4 p.m. Okay, well, at 4 p.m., what's t equal to at 4 p.m.? What's the value of t? 4, that's right, Ian, because we started at noon, and 4 p.m. is 4 hours later. So t is 4 hours. So that means that x, which is the distance that ship A has sailed going east, we would, well, the ship A travels at 35 kilometers per hour, and if it does that for 4 hours, it's gone 140 kilometers. Similarly, ship B that travels north at 25 kilometers per hour, well, after 4 hours, it's gone 100 kilometers. So this allows us to get the x and the y. And by the way, we know dx dt and dy dt. We know the rates at which these ships sail. Are there any questions so far? Is there any variable that we still need to find? You know, keep in mind, we want to solve for dz dt, right? So is there any other variable that we need to find a value for in this equation here? That's right, Lynn. Very good. We got to find what z is. We can do that. We can do that because remember that by the right triangle, you had that the quantity 150 minus x squared plus y squared equals z squared. Okay, well, maybe I'll write it in here. 100, we had that 150 minus x. Well, I'll write it like this: z squared is equal to 150 minus x squared plus y squared. Okay, and so to solve for z, we're just going to take the square root of both sides. Okay, this came from the Pythagorean theorem. So if we take the square root of both sides, we're going to get then z equals plus square root of 150 minus 140 squared plus 100 squared. As remember, x is 140 and y is 100. And I included the units just so you can see that, you know, it makes sense. So z will be the square root of 10,100 meters. And you notice when we did the rates up here, I'd like to include units sometimes when I do my computations, because like x is a distance. So if I take the rate 35 kilometers per hour, multiply by 4 hours, I get a distance. It just kind of gives me a comfortable feeling to when I do this. Now, one thing here, one moment. My unit should be kilometers, right? Not meters. So this should be kilometers. Okay, kilometers. Okay, so a little, it's, just, I'll adjust that on my, my paper as well. Are there any questions so far? Now you notice I keep the square root, z is equal to the square root of 10,100. I don't write that as a decimal. I do not write that as a decimal yet, because WebAssign's very picky about it wants exact answers, or if it says, like, for instance, round to the nearest decimal, it's going to want something very close to exact answer. So you don't want to, you want to round, basically. Normally you want to round your answer at the very end. Hey, it's no problem that z equals the square root of 10,100, and I'm just going to plug that in up here for z. Okay. All right, I'll move to the next page unless there are any questions. Are we good so far? Okay. All right, thank you, everybody. Then let's move to the next page. Okay. And I'm let me see here. So, okay, so now, what I'm going to do is I'm going to solve the differential equation. I'm going to solve this related rates equation. And they call it related rates because you're taking rates, like you're taking a rate with respect to z and relating it to a rate with respect to y and a rate with respect to x through an equation. Hence, it's a related rates equation. And I could plug in the values right now in this equation here and solve for dz dt. But also, I could, divide through this equation by 2, okay, and I could write the first factor here as 2 times x minus 150. I could, 150 minus x is the same as negative 1 times x minus 150. And I do that because that gets me a positive 2 here out in front and of the dx dt. And then I divide by 2, and I just then can write dz in a little bit nicer form. dz dt, I should say. But again, I could have put in the values right here. People will do it differently. I tend to favor, I don't know, I sometimes like, I know I'm looking for dz dt. So, okay, let me get the formula for dz dt and then plug in the values. But people are different. People are different. Now you substitute the values. Okay. And, we know that x is 140. Okay, we know that x was 140. Now this is at t equals 4 hours, right? This is at 4 p.m. The distance boat A sailed east is 140 kilometers. It's sailing at a rate of 35 kilometers. Boat B has traveled a distance of 100 kilometers north, and it's traveling at a rate of 25 kilometers per hour. And distance z is 10,100, square root of 10,100 kilometers. So this gets me down to here. Okay. All right. So are there any questions so far? Just let me know. All right. If we're good, then let's move to the next page if we're good. Like to be sure I'm pacing myself okay. Hold on. Whoa. Yaki says, why is 2 canceled? Well, all I did was, you see, if I divide, all right, so Yaki's asking about this step here, going from this step to this step. If I divide everything by 2, that gets me to this step here. Yaki, are you comfortable with that? Okay, very good. Are there any other questions? All right. Well, then let's proceed on. So now we have a value for dz dt. This value on the left, but I could type that in WebAssign, but why not try to simplify the answer? So I do so. So the numerator, which is 40 minus 150, the quantity, well, the numerator is negative 10 times 35 plus 2,500. That equals 2,150. And I'm dividing by that by the square root of 10,100. And I noticed that in the denominator, 10,100, I noticed that, 100 goes into that. So, and 100 is a nice square root number. So I'm going to write the square root of 10,100 as the square root of 100 times 101. That's no big deal. Just take 10,100 and divide it by 100 on your calculator. Or you could do it in your head. You get 101. And so the square root of 100 times 101 is 10 times the square root of 101. And this would be the exact answer. 2150 divided by 10 times the square root of 101. However, if WebAssign wanted you now to round to the nearest 10th decimal place, that would give you 21.4 kilometers per hour. And that is how fast the distance is changing. How fast that is, 21.4 kilometers per hour is the distance. I'm not saying this right. Therefore, at 4 p.m., the distance between the ships is changing at a rate of 21 kilometers per hour. And the rate of change is less than the individual rates at which the boats sail east and west. That makes sense because the hypotenuse is longer. The distance between the boats is longer than it's longer than the legs of the hypotenuse. Got to be a little careful how I phrase that. There could be, counterexamples to that, but it makes sense. Okay, so, all right, one moment. All right, so are there any questions at all? All right, Betsu is good. How many think this is? I mean, I mean, word problems. I know generally students don't like word problems, but word problems are what come up in life, in real life. Um, how many think this section 4.1 is kind of cool? At least the problems that you're able to do. How many think? I mean, it's not an easy section, maybe, but how many think it's kind of cool the problems that you're able to do, given your knowledge of calculus? But Sue likes some of them, so yes, there are a different variety, aren't there? And all right, and yep. So I hope more than Betsua though likes some of the problems. I hope we might have a few more a few more students who. Okay, all right. Thank you, John. Thank you, Lynn. Lynn thinks it'll be useful. Absolutely, absolutely, absolutely. All right. Well, let me put a stop there.